Okay, so are you ready to dig into some serious Earth history?
I am so ready.
Because you have provided us with an absolute ton of fascinating material.
Yeah.
And we're talking about everything from the Big Bang to the ground beneath our feet.
Literally everything.
So it's a pretty big topic.
It is a big one.
Um, but don't worry, because we're here to kind of sift through it all and pull out the most mind-blowing parts.
The coolest stuff.
It'll be like we're kind of exploring Earth's greatest hits together.
I like that. Yeah.
Yeah.
Earth's greatest hits.
So to help us do that, we have with us a specialist in deciphering Earth's history
That's me.
who can help us connect the dots.
Yeah, and what's really cool is we're not just talking about events in the distant past. These events are the reason why our planet is the way it is today.
It's true. It's like having a backstage pass to the creation of everything.
I like that too.
I'm on a roll.
Yeah.
So let's rewind back to the very beginning, like way, way back to the Big Bang.
Okay.
Most people have heard the name, but it's more than just a catchy title.
Right. Absolutely.
Like, what actually happened? It's more than a theory. It's like, so think of it like this. Imagine an ambulance siren.
Okay.
As the ambulance rushes towards you, the sound waves are compressed, making the pitch higher.
Right.
As it moves away, the sound waves stretch and the pitch gets lower.
Huh?
That's essentially what we see with light from distant galaxies.
Oh.
It's stretched, or redshifted, telling us those galaxies are moving away from us and the universe is expanding.
So the universe is kind of like a balloon that's constantly being inflated.
Exactly.
And we're all just along for the ride. That's what this redshift tells us. And that constant expansion points back to a single point of origin, which is where the Big Bang theory comes in. And there's even more to support that, like the cosmic microwave background radiation. All right. Basically an afterglow of the Big Bang that we can still detect.
Wow, an afterglow that's been traveling for billions of years. Talk about old light.
Yeah!
Okay, so we've got this massive explosion that kicks off the universe, but it was mostly hydrogen and helium, right?
Yeah.
Not exactly the recipe for a planet like Earth.
You're right. The Big Bang alone didn't create all the elements that we see around us. For that, we need to turn our attention to the stars, giant element factories in space.
Wait, so stars are creating the stuff that makes up, well, everything.
Exactly.
That's a big job.
Big job, yeah. Through a process called nuclear fusion, the intense pressure and heat at the heart of a star fuse later elements into heavier ones, releasing tremendous energy in the process. It's like a cosmic pressure cooker.
Wow.
This fusion is what makes stars shine, and more importantly, creates the building blocks of planets and even ourselves.
So the carbon in our bodies,
Yeah.
the silicon in our computers, that all came from stars.
It all comes back to stars.
That's kind of poetic when you think about it.
It is.
But stars don't last forever, do they?
You're right. When a star runs out of fuel, its fate depends on its size. Smaller stars, like our sun, will eventually expand into red giants, then shed their outer layers, leaving behind a white dwarf, sort of like a stellar retirement plan.
Right.
But the really massive stars, those go out with a bang, literally.
Right. Here come the supernovas. Weren't those explosions absolutely crucial for creating the heavier elements?
You got it. Supernovas are the universe's most spectacular fireworks show. And they're not just dazzling, these explosions scatter heavier elements, like gold and uranium, throughout space.
So the gold in my jewelry, or the uranium used in nuclear power plants, those were forged in the heart of a dying star billions of years ago.
Billions of years ago, that's right.
That's mind-blowing.
That's a beautiful cycle.
It's like a cosmic recycling program from exploding stars to new solar systems.
Right.
Speaking of which, how do we go from scattered star stuff to an organized solar system like ours?
That's where the nebular hypothesis comes in. Imagine a giant swirling cloud of gas and dust left over from those supernovas.
Okay.
Gravity pulls this material inward, causing it to spin faster and flatten into a disk. At the center, the material clumps together, heats up, and eventually ignites. A new star is born.
A new star is born.
Further out in the disk, the leftover gas and dust start to stick together, forming larger and larger clumps, the beginnings of planets.
Okay, that makes sense. But why are the inner planets, like Earth, rocky, while the outer ones are gas giants? Was it just a cosmic coin toss?
Not quite. It all comes down to temperature. Closer to the sun, where it's much hotter, only heavier elements like iron and silicon could condense to form those rocky planets.
Oh.
Further out, the temperatures were cold enough for lighter elements like hydrogen and helium to condense, which is why we have those massive gas giants like Jupiter and Saturn.
So our place in the solar system, the makeup of our planet, it's all thanks to where we ended up in that spinning disk of cosmic debris.
It's all about location, location, location.
Location, location, location.
Even in space.
That's amazing. But what about the asteroid belt? Is that just a leftover construction zone from the early solar system?
It's more than that. Imagine a planet trying to form near Jupiter, but its immense gravitational pull kept pulling it apart. That's essentially what we think happened with the asteroid belt. Those asteroids are like time capsules, remnants from the solar system's formation.
So we've got our star, our planets, and even some leftover building blocks.
We do.
It's starting to look like a solar system.
It's all coming together.
But what about Earth itself? What was it like in those early days? I'm guessing it wasn't exactly a tropical paradise.
You are correct about that. In the beginning, during what we call the Hadean Eon, was a wild place. Picture a planet partially covered in molten rock, bombarded by asteroids, with volcanoes erupting everywhere, about as far from a vacation spot as you can get.
Yeah, I think I'll skip that trip.
Yeah.
It's hard to imagine that fiery chaos eventually becoming the Earth we know today. So how did that happen? Where do we even start?
Well, to understand how Earth transformed, we need to look at one of its most defining features, the moon. Have you ever wondered why it always shows us the same face?
Now that you mention it, yeah, it is kind of strange that the moon always seems to be staring at us with the same side.
Yeah.
Is there something about the way it spins or something?
It's not just a weird coincidence, it's actually a clue to how the moon formed. Imagine this. Early Earth, still a fiery mess, gets slammed by a Mars-sized object. We're talking a cosmic collision of epic proportions.
Wait, a Mars-sized object? That's insane. It's no wonder early Earth wasn't exactly a peaceful paradise.
Right. This theory, called the giant impact hypothesis, explains why the moon always shows us the same face. That massive impact blasted a huge chunk of Earth material into space, which eventually clumped together to form the moon. The impact also knocked Earth slightly off kilter, giving us our seasons, and sped up its rotation, shortening our days. Talk about a life-altering event.
So our seasons are day length, all because of a giant cosmic smash-up billions of years ago. That's wild. But there's more to this impact theory, right? What's the evidence?
It's like a cosmic detective story, and the evidence is compelling. If you analyze the composition of Earth rocks and moon rocks, they have nearly identical ratios of certain elements, like fingerprints at a crime scene. This suggests they formed from the same source material.
Okay, that makes sense. So this giant impact created the moon. But what about all those asteroid impacts we hear about? Didn't Earth go through a period of getting pummeled by space rocks?
You're talking about the late heavy bombardment. Remember those gas giants we talked about earlier, Jupiter and Saturn?
Yeah.
Well, it turns out their massive gravity acted like a cosmic pinball machine, flinging asteroids and comets all over the early solar system.
So instead of a nice calm period after the moon formed, Earth was basically used for target practice. That's rough.
Pretty much. It was a wild time in the solar system. But amidst all this chaos, something incredible happened. The stage was set for life to emerge.
From fire and fury to life. That's quite the plot twist. But how did life even stand a chance in that early Earth pressure cooker?
That's one of the biggest questions in science. We've found evidence of single-celled organisms like cyanobacteria in rocks that are over 3.5 billion years old. Imagine these tiny organisms thriving in a world that would be toxic to us.
Life finds a way, right? But where did those first cells come from? Did they just magically appear?
There's no magic involved, just some really interesting chemistry. One idea is that life originated in those hydrothermal vents we talked about earlier, those hot springs on the ocean floor spewing out chemicals from deep inside Earth.
You mean those same vents that are teeming with bizarre creatures today?
The very same. These vents are like oases in the deep sea, providing the energy and nutrients that life needs to thrive, even without sunlight. It's possible that similar vents billions of years ago acted as the cradles for those very first life forms.
So life might have started in these extreme environments, powered by chemicals instead of sunlight. That's amazing. But those were just single-celled organisms, right? How did we go from microbes to the diversity of life we see today?
Well, those early microbes, specifically the cyanobacteria, were busy changing the planet in a big way. They were producing something that would change the course of life. Oxygen.
Oxygen. You mean like the stuff we breathe? But wasn't early Earth's atmosphere toxic to us?
Exactly. Back then, there was very little free oxygen in the atmosphere, but these tiny cyanobacteria were photosynthesizing, taking in carbon dioxide and releasing oxygen as a byproduct.
So those tiny organisms were pumping out oxygen slowly but surely, changing the very air we breathe. It's like Earth's very own terraforming project.
That's a great way to put it. And over millions of years, this oxygen began to accumulate in the oceans and then in the atmosphere, leading to what we call the Great Oxidation Event, or GOE for short.
That sounds like a pretty big deal. Was it all smooth sailing from there, or did this oxygen revolution cause some problems?
Well, imagine you're an organism that's used to a world without oxygen. Suddenly, this reactive gas starts appearing everywhere. For many early life forms, oxygen was toxic, and the GOE led to a mass extinction.
So one organism's waste product is another organism's downfall. A tough break for those early microbes.
That's evolution for you. But for those organisms that could tolerate oxygen or even use it for energy, it was a game changer.
It's like oxygen opened up a whole new level in the game of life. It allowed for more complex life forms to evolve, eventually leading to wellness.
You got it. The GOE was a pivotal turning point. And as oxygen levels rose, it also had a dramatic impact on Earth's climate.
Okay, so we've got oxygen, we've had mass extinctions. What else did this great oxidation event have in store?
Remember those banded iron formations, those distinctive layers of red rock we find all over the world?
Those are stunning. I remember seeing pictures of them. They look like giant layers of tiramisu.
Well, those layers are like a geological history book, and they tell the story of the GOE. As oxygen filled the oceans, it reacted with dissolved iron, creating massive deposits of iron oxide, essentially rust on a planetary scale.
So those stunning rock formations are a direct result of this oxygen revolution. That's incredible.
It is. And the GOE didn't just impact the rocks, it also had a chilling effect on the planet, literally.
A chilling effect. You mean like an ice age?
You got it. Oxygen reacted with methane, a potent greenhouse gas, removing it from the atmosphere. This caused a global cooling event, potentially triggering Earth's first glaciation, the Uranian glaciation.
Wow, so these tiny microbes, by pumping out oxygen, accidentally caused a global ice age. Talk about unintended consequences.
Earth's system is all about interconnectedness. One change can ripple through the entire planet, but the story doesn't end there. As we move further along, the planet thawed and life continued to evolve. And during the late Proterozoic eon, another major geological event took place, the formation of a supercontinent called Rodinia.
Wait, a supercontinent? You mean like all the continents we know today mashed together like a giant jigsaw puzzle?
Exactly. Imagine all that landmass, a single giant continent surrounded by a vast global ocean.
That's mind-boggling. What happened to Rodinia? Did it just stay put, or did things get shuffled around again? So we've got this supercontinent Rodinia just hanging out there for millions of years. But knowing Earth's track record, I'm guessing it didn't stay put forever.
You know how much Earth loves a good continental drift? Rodinia eventually broke apart, leading to the formation of new oceans, new coastlines, and a whole new set of possibilities for life.
Okay, so continents are rearranging themselves, life is evolving. Are we getting close to the part where things start to look a bit more familiar?
We're getting there. The breakup of Rodinia set the stage for the Phanerozoic eon. That's the eon we're in right now, and it's called the Age of Visible Life for a reason. This is where we see the explosion of diverse, complex life forms that fill our planet today.
Bring on the dinosaurs. That's what I'm talking about. But before we get to those prehistoric celebrities, what was happening in the first era of the Phanerozoic, the Paleozoic?
The Paleozoic was like a giant experiment in evolution. Life really took off in the oceans with the rise of fish trilobites and all sorts of bizarre creatures we can barely imagine today.
Okay, you've got to give me an example. What kind of bizarre creatures are we talking about?
How about a giant sea scorpion with a stinger as long as your arm?
No way! Are you serious? That's both awesome and terrifying.
Those were just some of the amazing creatures that inhabited the Paleozoic oceans. And on land, things were getting interesting too. Plants started to colonize the land, creating the first forests, and then came the amphibians venturing out of the water for the first time.
So life was getting a foothold on land. Were those early amphibians anything like the frogs and salamanders we see today?
They were the ancestors of everything we see hopping and slithering around today. But imagine them, larger, clumsier, still figuring out this whole living on land thing.
I can picture it. So
Yeah.
life is spreading, evolving, things are changing. But what about the continents? Were they still doing their own
Yeah.
thing?
Well, towards the end of the Paleozoic, something incredible happened. Remember how we talked about Rodinia, that supercontinent? Well, get ready for round two, because by the end of the Paleozoic, almost all the land masses on Earth had collided again to form another massive supercontinent, Pangaea.
Another supercontinent. It's like Earth just can't resist putting all the pieces back together again, can it?
It's a cycle of coming together and breaking apart. And the formation of Pangaea had a huge impact on life. Imagine vast deserts stretching across the interior of the continent while the coasts were teeming with life.
It's incredible how these massive geological events shape the evolution of life. But I know Pangaea didn't last forever, which brings us to the Mesozoic era, right? The age of dinosaurs.
Get ready for some prehistoric star power. The Mesozoic was the reign of the dinosaurs, from the massive long-necked sauropods to the fearsome predators like Tyrannosaurus rex.
It's funny to think that those creatures we're so fascinated by today were just going about their lives completely unaware that they become legends. What was it about the Mesozoic that allowed dinosaurs to thrive?
Well, remember how Pangaea formed at the end of the Paleozoic? Well, during the Mesozoic, Pangaea started to break apart again. This led to the creation of new seas, inland climates became less extreme, and new ecological niches opened up.
So a changing world provided opportunities for dinosaurs to diversify and evolve. It makes you wonder what those ecosystems were like. What would it have been like to walk through a Mesozoic forest?
Picture this. You're walking through a human forest, giant ferns tower overhead. The air is thick with the scent of pine and damp earth. You hear a low rumble in the distance, and then you see it, a Brachiosaurus, a dinosaur so tall it could probably look into a fourth-story window lumbering through the trees.
That's an image I won't soon forget. But the dinosaurs didn't rule forever, did they? What happened? Was it just a slow decline, or was there a more dramatic ending?
The Mesozoic was a long and dynamic era, but it came to a dramatic end about 66 million years ago with the KPG extinction event, which wiped out about 75% of all plant and animal species on Earth, including the non-avian dinosaurs.
That's the one caused by an asteroid impact, right?
Yeah.
It's crazy to think that a single event could have such a devastating impact on the entire planet.
It was a planet-altering event. Imagine an asteroid about 6 miles wide slamming into Earth near the Yucatan Peninsula. The impact unleashed earthquakes, tsunamis, and wildfires on a global scale. The dust and debris thrown into the atmosphere blocked out the sun, causing a global cooling effect that lasted for years.
Well, talk about a bad day for Earth. It's hard to imagine anything surviving that kind of catastrophe.
It was a challenging time for life on Earth. But remember, life is incredibly resilient. And in the aftermath of this mass extinction, a new era began. The Cenozoic, also known as the Age of Mammals.
And this is where our story really starts to take shape. So with the dinosaurs out of the picture, what happened? Did mammals just inherit the Earth and get to work?
It wasn't quite that simple. In the wake of the extinction, many ecological niches were left vacant. Mammals, which had been relatively small and inconspicuous during the Mesozoic, were now presented with a huge opportunity.
It's like the planet went through a reset and mammals were ready to take advantage of the new playing field.
Exactly. Over millions of years, mammals diversified and evolved to fill those empty roles, eventually leading to the incredible variety of mammals we see today, from whales to bats to whales.
And that brings us to the final chapter of our deep dive. Humans. It's amazing to think about the incredible chain of events, the billions of years of Earth's history that paved the way for our existence. So how do we fit into this grand narrative?
Well, the story of human evolution is a fascinating one. It started millions of years ago with a group of primates that began walking upright in Africa. These early hominids were our ancestors, and over time they evolved and diversified, leading to the emergence of our own species, Homo sapiens, about 300,000 years ago.
So from those early hominids walking across the African savanna to us sitting here today discussing billions of years of history.
Yeah.
It's mind-boggling, isn't it?
It really is, and it's a reminder that we are a part of this planet's story, a product of billions of years of evolution and change.
It's humbling to think about the vastness of geologic time, the incredible events that have shaped our world, and the remarkable journey that life has taken. And it really makes you wonder about our place in it all and what stories our planet will tell about us millions of years from now. Thanks for joining us for this incredible deep dive, and until next time, keep exploring.